we have all been taught the same story since we were children. That around 13.8 billion years ago, out of absolutely nothing, the entire universe was born. That this was the moment space itself began, the moment time started to tick, the moment our whole story opened. We call it the Big Bang, and for 100 years, it has been the most trusted story we have. But in just the last few years, 3 cracks have appeared in that story, and they have started to keep scientists awake at night. The first crack is the most unsettling. There is a force pushing this entire universe apart, and we call it dark energy. For 25 years, we have believed it never changes. The same everywhere, the same for all time. But the largest map of the cosmos we have ever made is now hinting at something else. It looks like that force may be slowly growing weaker, and if that is true, then the end of the universe will not be the end we always imagined. The second crack came when we pointed our most powerful telescope at the oldest corner of the universe, and there we found a galaxy that simply should not have existed yet. Too bright, too large, far too grown up for how young the universe was at the time. And the third crack strikes at one of our deepest rules of all. We have found 2 structures in the sky so enormous that, by our own laws, they should not be possible. Now on its own, not one of these discoveries proves the Big Bang wrong. But when you lay all 3 on the same table, a deeper question begins to rise. What if the Big Bang was not a beginning that came out of nothing? What if it was not the beginning at all? So tonight, we are going to look at all 3 of these cracks up close. Then we are going to travel backward in time, all the way to that first moment, the place where our mathematics simply gives up. And finally, we are going to reach the bold ideas that dare to say something existed even before that first moment. But let me make one thing clear right at the start. The first half of this journey is real, measured data. The second half is still only theory. Some of it beautiful, some of it daring, but none of it proven. And I will tell you, at every single step, exactly where we are standing. I will never hand you a guess and call it the truth. And before we begin, one small thing. I have noticed that many of you come back for these journeys, but have not yet subscribed. If you would like to keep exploring the deep questions of the cosmos with us every Wednesday and Sunday, just subscribe and turn on the bell so the next one finds you. Now settle in, let the day fall away, and let us start with the first crack, the one that may run the deepest of all. So let us start with the first crack, which is maybe the deepest of the 3. And its story begins back in 1998. At that time, 2 separate teams of scientists were measuring the light of distant, exploding stars. They were trying to answer what seemed like a simple question. How much is the expansion of the universe slowing down? Everyone expected it to be slowing, and for a good reason. All the matter in the universe pulls on all the other matter through gravity, and gravity should be gently putting the brakes on the expansion, like the Earth tugging a ball back down after you throw it. But the answer stunned everyone. The universe was not slowing down at all, it was speeding up. Sit with how strange that is. It is as though you threw a ball into the air, and instead of falling back, it shot upward faster and faster into the sky. Something was fighting against gravity. Something was pushing the entire universe apart. We had no idea what it was, so we gave it a name, dark energy. And this is not some small background detail. When you add it all up, dark energy makes up around 70% of everything in the universe. More than 2/3 of all the energy that exists is this one mysterious force we cannot see, cannot touch, and cannot explain. Now here is the belief that sits at the very center of our story. For decades, our most trusted model of the universe has assumed one thing about dark energy, that it never changes, not with time, not from place to place. A fixed, frozen, unchanging force spread evenly through every corner of space. Scientists call this idea the cosmological constant. and almost our entire picture of the universe rests on it. And that assumption is now being challenged by a machine. Its name is DESI, and it has one job: to build the largest three-dimensional map of the universe ever made. It is a massive effort, bringing together more than 900 scientists from over 70 institutions. Every clear night, DESI captures the light of thousands of galaxies and measures how far away each one is. But the map it builds is no ordinary map, because the light from distant galaxies takes billions of years to reach us. So looking farther out into space means looking farther back into time. DESI is really building a map of history. The deeper it looks, the younger the universe it sees. And in March of 2025, DESI released the result of its first 3 years of work. This map included around 15 million galaxies and quasars. With it, scientists could trace the effect of dark energy across the last 11 billion years, step by step, and what they found shook them. It looked as though dark energy has not always been the same. In the distant past, its push seems to have been stronger, and over time, it appears to be slowly growing weaker, as if someone were very gently easing their foot off the accelerator of the universe. And here is what makes this even harder to dismiss. This same hint first showed up in 2024, in DESI's very first year of data. Back then, many people assumed it was just noise, a fluke that would quietly vanish once more data came in. But the next year, when the data more than doubled, the hint did not vanish. It grew stronger, and in science, that is one of the biggest signs that something might truly be real. But here, I have to be completely honest with you, because this matters. This is not proven. DESI's data, on its own, still fits our old model just fine. The hint only appears when you combine it with other measurements. The ancient light of the Big Bang, those exploding stars, the bending of light across the cosmos. And it has not yet reached the strict level of certainty that scientists demand before calling something a discovery. One scientist on the team said plainly that it would be too soon to say for sure. But another scientist on that same team said something that stays with you. He said the simplest explanation for what we are seeing is starting to shift. And if this turns out to be true, the meaning is enormous. It means the fate of our universe will not be what we always believed. But this was only the first crack, and it was a crack in our own time. The real shock came when we turned our most powerful telescope toward the oldest corner of the universe. And there, we found something that had no business being there. That is where we go next. So now we come to the second crack, and it takes us to the oldest, most distant corner of the universe. Remember what we just learned. The farther away you look, the further back in time you see. So if we want to look at the universe as a newborn, we simply have to look far enough away. And to do exactly that, we built the most powerful telescope humanity has ever made, the James Webb Space Telescope. Here is something worth understanding about how it works. When light travels for billions of years across an expanding universe, it gets stretched along the way. Light that started out blue or white is pulled longer and longer, until by the time it reaches us, it has become infrared, a kind of light our eyes cannot see. James Webb was built for precisely this. It sees in infrared, and that is why it can reach galaxies that stayed hidden in the dark for every telescope before it. And with that power, James Webb found a galaxy that has puzzled scientists across the world. Its name is not poetic, they call it MOM-Z14, but what it represents is staggering. First, understand how old this galaxy is. We are seeing it as it was when the Big Bang had happened only about 280 million years earlier. That means the entire universe was just 2% of its current age. If you imagine the whole history of the universe as a single human life, this is a baby in its first week. And in that newborn universe, this galaxy already existed. But simply existing is not the shocking part. The real puzzle is what it was like. Because this galaxy was bright, startlingly, impossibly bright. It was large, and strangest of all, it was already rich with heavier elements, the kind that should take generations of stars to build. Let me explain why that last part matters so much. After the Big Bang, the universe contained only the lightest elements, mostly hydrogen and helium. The heavier ingredients, the ones that make up planets and rocks and living things, do not come from the Big Bang. They are forged deep inside stars, and they are only scattered out into space when those stars grow old and die. So building up heavier elements takes time. It takes a whole generation of stars to be born, to live out their lives and to die. But this galaxy already held those elements at just 280 million years old. It is like looking at a newborn baby and finding it already has a full set of teeth and grey hair. Our computer models simply cannot make this much happen this fast. And it is not a single strange exception. Scientists confirmed MOMZ14 carefully, using James Webb in a survey led by the astronomer Rohan Naidu. They gave that survey a wonderful name. They called it Mirage or Miracle because they were asking exactly the right question. Were these impossibly early galaxies just an illusion in the data, a mirage, or were they real, a genuine miracle that breaks our understanding? And the answer came back, MOMZ14 is real. It is not a mirage. Even more, it is not alone. When scientists counted galaxies in that ancient era, they found far more of these bright, massive, grown-up galaxies than they ever expected. And this record holder is only the current one. Each year, James Webb seems to find something even older, even farther, even harder to explain. Now here, I have to be honest, the same way I promised. This does not mean the Big Bang is wrong. What it means is that our understanding of how galaxies form has a gap in it. Maybe the very first stars were far larger and burned far faster than we thought. But there is another possible answer, and it is much deeper. Maybe these galaxies simply had more time to grow than we believed was available. And if that is true, it raises a quiet, unsettling thought. It suggests the clock of the universe may have been ticking even before that first moment we call the beginning. So already, two of our cracks are pointing in the same strange direction toward the beginning itself. But before we follow them there, one crack remains, and it is the largest of all. So vast that its very existence breaks one of the deepest rules we have. That is where we go next. So now the third crack, which may be the strangest of all, and it strikes directly at one of our deepest rules. Here is that rule. Our entire understanding of the cosmos rests on one clean assumption, that if you look at the universe on a large enough scale, it should look the same in every direction, everywhere. On small scales, sure, it is messy. Here, a crowd of galaxies, there, an empty void. But as you pull back far enough, all that messiness should blur together into something smooth and even. Think of flying over a forest in a plane. From up there, you just see a smooth green carpet. Down on the ground, every tree is different, every bush is its own shape. But from that height, they all melt together into one even blanket. We expect the universe to behave the same way. Scientists even set a limit for this. By their rules, no single structure larger than about 1.2 billion light-years should be able to exist. Above that size, everything should just be smooth. But over the past few years, a young researcher has watched that limit break not once, but twice. Her name is Alexia Lopez, and she was doing her research at the University of Central Lancashire. She was studying the light of distant quasars, those blazing cosmic beacons whose light travels billions of years to reach us. As that light crosses the universe, any matter in its path leaves a faint mark on it. And by reading those marks, you can map giant structures hidden in the dark. In 2021, using this method, she found the first one, a vast curved line of galaxies shaped like an enormous arc. It was named the Giant Arc, and it stretches about 3.3 billion light-years across, nearly 3 times larger than the limit that was supposed to be impossible. That alone was a serious problem, but the real shock came in January of 2024. The same team found another structure in almost the very same patch of sky. This one was a huge, nearly complete ring of galaxies. They called it the Big Ring. Its diameter is about 1.3 billion light-years, and if you traced its full circumference, it would run some 4 billion light-years around. But the strangest part of the whole story is this. These two giant structures are not just both too big. They sit in the same region of the sky. They lie at almost exactly the same distance from us, around 9.2 billion light-years away. So we are seeing them in the same era of cosmic history, when the universe was roughly half its current age. And in the sky, they sit only about 12 degrees apart. On a cosmic scale, these two impossible giants are next-door neighbors. Alexia Lopez put it in very plain terms. She said that neither of these structures can be easily explained by our current understanding. By her account, finding even one of them anywhere in the observable universe should have been astonishing. But here there are two sitting side by side. So what does it mean? And here, honesty matters, because this case is not closed. Some scientists argue these may not be real structures at all, but tricks of the eye. When you go hunting for shapes in a map of billions of points, sometimes your brain finds patterns where there is only chance. Others think the Big Ring might be connected to ancient sound waves from the early universe, whose imprint still lingers in how galaxies are spread out today. But Lopez and her team, in a detailed review in 2025, argued that both structures are larger than the allowed limit, and that ignoring the two of them together is difficult. So now we have 3 separate cracks in front of us, one from our own time, one from the universe's infancy, and one in its very largest structure. Alone, not a single one of them proves anything. But when you place all 3 on the same table, a pattern begins to emerge that is hard to ignore. And that pattern is exactly what we are going to look at next. Because the real question is not whether any single crack is real. The real question is what happens when you stand back and look at all of them at once. Are these small cracks that better data will quietly fill? Or are they the first signs that our whole picture needs to be rewritten? History, as it turns out, has faced this exact choice before, and that is where we go next. So we have 3 cracks on the table, and the real question is what kind of cracks they are, because history has faced this exact moment before, and it turned out there are 2 very different kinds. To see the difference, let me tell you 2 short stories about the same thing, a wobble in the path of a planet. The first story is about the planet Uranus. In the 1800s, astronomers were tracking its orbit, and something was wrong. Uranus was not moving quite the way the laws of gravity said it should. There was a small, stubborn wobble that the math could not explain. Now, this was a crack. The rules seemed to be failing. So what did scientists do? A mathematician named Urbain Le Verrier made a bold bet. He assumed the laws of gravity were perfectly correct, and that the wobble must be caused by something we simply had not seen yet. An unknown planet out there in the dark, tugging on Uranus with its gravity. He did the math, and he predicted exactly where this hidden planet should be. In 1846, astronomers pointed their telescope at that precise spot in the sky, and there it was, a brand new planet right where he said it would be. We named it Neptune. Think about what happened there. The crack was real, but it was not a sign that the rules were broken. It was a sign that a piece was missing. Once they found the missing piece, the rules worked perfectly again. The crack got filled, and our old laws stood stronger than ever. Now the second story, And it is about another wobble, this time in the orbit of Mercury, the closest planet to the Sun. Mercury also refused to move quite the way it should. There was a tiny, unexplained shift in its path, and it looked like exactly the same kind of problem as Uranus. So naturally, scientists tried the same solution that had worked so beautifully before. They assumed there must be another hidden planet, this time between Mercury and the Sun, tugging on it. They even gave this planet a name before they found it. They called it Vulcan, and they searched for it for years. But no matter how hard they looked, Vulcan was not there. The trick that had found Neptune simply failed. For decades, that little wobble in Mercury sat there, unexplained, until 1915, when a man named Albert Einstein looked at it in a completely new way. Einstein said the problem was not a missing planet. The problem was gravity itself. Our very understanding of gravity, the one written by Isaac Newton, was incomplete. Einstein rewrote it from the ground up, describing gravity not as a simple force, but as the bending of space and time. And when he used his new theory to calculate Mercury's orbit, the wobble was explained perfectly. There was no hidden planet, there had never been. Instead, one of the deepest rules in all of physics had just been replaced by something deeper. So now you can see the two kinds of cracks. Sometimes a crack means a piece is missing, like Uranus and Neptune. You find the missing piece, and the old rules survive. And sometimes a crack means the rules themselves are wrong, like Mercury and Einstein. No missing piece exists, and the only way forward is to rebuild our understanding from scratch. And this is the exact choice we face today, with our three cracks: dark energy weakening, galaxies too old for their age, structures too big to exist. Maybe these are Neptune cracks. Maybe there is a missing piece we simply have not found yet. And once we do, our standard picture of the Big Bang will stand stronger than ever. That is entirely possible, and many scientists believe it. But maybe, just maybe, these are Mercury cracks. Maybe they are quietly telling us that our deepest assumption, the idea that everything began at the Big Bang and nothing came before, is the thing that needs to be rewritten. And right now, honestly, no one knows which kind of crack we are looking at. To even begin to answer that, we have to do something bold. We have to stop looking outward and instead travel backward, all the way back to that very first moment, to the Big Bang itself, and the instant right at the edge of it where our mathematics stops working entirely, because it is there, at the beginning, that we will find our first real clue about whether anything came before. That is where we go next. So let us travel backward all the way to the beginning, and to do it, we just run the story of the universe in reverse. Right now, the universe is expanding, everything spreading apart, so if we play that backward, everything comes together instead. Rewind the film, and the galaxies rush toward each other. Keep rewinding, and everything grows closer and hotter and denser. The whole universe shrinks and heats up, like gas being squeezed tighter and tighter inside a smaller and smaller container. Keep going back, past the first stars, past the moment atoms formed, into a universe that is a searing, crushing fog, and still we rewind. The universe becomes smaller than a galaxy, smaller than a star, smaller than a planet, smaller than a single room, smaller than a grain of sand. Everything that exists, every star and every galaxy that will ever be, all of it squeezed into a space almost too small to imagine. And then we reach the very edge, the first instant, and here, something breaks. When scientists rewind their equations all the way to that first moment, the numbers do something alarming. The density of the universe climbs toward infinity. The temperature climbs toward infinity. Everything the math describes shoots up to infinity all at once. Scientists call this point the singularity, a single point of infinite density where all of space and time is crushed into nothing at all. Now here is the part that most people misunderstand, and it is important. When your equations suddenly spit out infinity, that is almost never a description of something real. In physics, infinity is a warning light. It is the math's way of raising its hands and saying, I have stopped working here. I cannot describe this, so the singularity is not really telling us that the universe truly became infinitely dense. It is telling us that our best theory has hit a wall and simply cannot see past it. So the real question becomes, why does the math break down at that exact moment? And the answer is one of the deepest problems in all of science. It comes down to two great theories, the two pillars that hold up modern physics. The first is Einstein's theory of gravity, which describes the biggest things in the universe. Stars, galaxies, the bending of space and time. It works beautifully, and it has passed every test we have ever thrown at it. The second is quantum mechanics, which describes the smallest things in existence. Atoms, particles, the tiny world beneath everything, and it too works beautifully, passing test after test. Here is the problem. These two theories almost never have to talk to each other. Gravity rules the huge and the heavy. Quantum mechanics rules the tiny and the light. In everyday life, and even across most of the universe, they stay politely out of each other's way. But at the very first instant of the Big Bang, something impossible happened. The entire universe, all its staggering mass and energy, was squeezed into a space smaller than an atom. And that is the disaster. Because now you have something incredibly heavy, which demands Einstein's gravity, packed into something incredibly small, which demands quantum mechanics. Both theories are forced into the same tiny room at the same time, and when they meet there, they do not agree. They contradict each other. The math falls apart into nonsense. This is the great unsolved problem that physicists have chased for a century. We do not yet have a single theory that can handle gravity and the quantum world together. A theory of everything, some call it, and without it, that first instant stays locked behind a wall we cannot cross. So this is where we truly stand. The singularity is not the answer. It is the sign of our own ignorance, the exact point where our knowledge runs out. And as long as our two great theories refuse to work together, that first moment, and anything that might lie beyond it, stays hidden from us. But scientists are not content to stand at a wall and simply stop, because some of them have started to build new theories, daring ideas that try to replace that broken singularity with something that actually makes sense. And the astonishing thing is that when they do, the wall sometimes seems to open, and on the other side of it, there may be something we never expected. Not nothing, but a before, and the first of those daring ideas is where we go next. So let us step through the wall for the first time, and I have to be clear right away. Everything from here on is theory. Bold, serious, carefully built theory, but not proven. So hold it lightly, and I will keep reminding you where we stand. The first idea comes from a physicist named Abhay Ashtekar, who works at Penn State, and it begins by questioning something we almost never question. What is space itself made of? We tend to imagine space as perfectly smooth, a continuous, seamless backdrop that you could divide into smaller and smaller pieces forever, without ever hitting a limit. But Ashtekar's theory, called loop quantum gravity, says something startling. It says space is not smooth at all. It says space is made of tiny, indivisible chunks. Little building blocks, so unimaginably small that you could never cut one in half. Space, in this view, is pixelated. Here is a way to picture it. Look at any photo on your phone screen from a normal distance. It looks perfectly smooth and continuous. But zoom in, closer and closer, and eventually you see it. The whole image is made of tiny squares, individual pixels. It only looked smooth because the pixels were far too small to notice. Ashtakar's theory says the universe is the same. Zoom in on space itself, far beyond the size of any atom, and you would finally reach the pixels of reality, the smallest possible pieces of space that can exist. Now, why does this matter for the beginning of the universe? Because it completely changes what happens when you rewind to that first moment. Remember the old problem. When you run the universe backward, everything is crushed toward a single point of infinite density. The singularity, the place where the math breaks. But that disaster only happens if space is smooth and can keep shrinking forever, down to nothing. But if space is made of pixels, it cannot shrink forever. There is a smallest possible size, a flaw. You cannot squeeze the universe smaller than a single pixel of space, because nothing smaller exists. And so, in this theory, the crushing collapse never reaches infinity. Instead, as everything is squeezed down toward that smallest size, something remarkable happens. The pixels of space start to push back. They create a powerful repulsive force, a kind of pressure that resists being crushed any further. And when the universe is squeezed to that absolute limit, this repulsive force becomes so strong that it stops the collapse entirely, and then it reverses it. The universe, crushed to its smallest possible size, is violently pushed back outward. It stops falling in, and it explodes back out. Do you see what that means? In this picture, the Big Bang was not the beginning. It was a rebound. Scientists call it the Big Bounce. And this changes the whole story. Because if our expanding universe is the result of a bounce, then something had to be there before it to do the bouncing. In Ashtakar's theory, before our universe was born, there was another universe, an older one, and that older universe was not expanding. It was collapsing, shrinking, falling inward under its own gravity, getting smaller and denser, until it reached that smallest possible size, hit the floor of the pixels, and bounced. And that bounce, that violent turnaround, is what we experience as our Big Bang. So in this idea, the answer to what came before is beautiful and simple. Before our universe, there was another universe, falling inward, that reached the bottom and bounced back out as us. The Big Bang was not a birth from nothing. It was a passage, a doorway from one universe into the next. Now let me keep my promise and be honest about what this is. Loop quantum gravity is a serious, respected theory, worked on by many brilliant scientists. But it is not proven. We have no direct evidence yet that space is truly pixelated. It remains one possible answer among several, a beautiful idea still waiting for the test that could confirm it or rule it out. But notice something. This theory gives us a before, but only one. One previous universe, one bounce, one doorway, and that raises an irresistible question. If it happened once, why only once? What if this bounce is not a single event, but something that has happened again and again and again forever? What if our universe is just the latest beat in a rhythm with no beginning? And that is exactly where the next theory takes us. So if the universe can bounce once, why not forever? This is where the next theory takes us, and it comes from a physicist named Paul Steinhardt at Princeton, working with his colleague Anna Ijs. Their idea is called the Cyclic Universe, and it is exactly what it sounds like. It says the universe is caught in an endless rhythm. It expands, then it contracts, then it bounces, and then it begins again, over and over, forever, with no first beat and no last. Let me walk you through one full cycle, because the way it works is elegant. Start with our universe, right now, expanding. Over unimaginable stretches of time, it keeps growing, spreading thinner and thinner until it becomes a vast, cold, empty darkness. In most stories, that is the end. But not here, because in this theory, after that long emptiness, the expansion very slowly grinds to a halt. And then, gently, it reverses. The universe begins to contract. It starts falling back inward, slowly at first, then faster, growing warmer and denser again, until it reaches that smallest possible size and bounces, exploding outward into a brand new universe. And then the whole cycle starts over. Expansion, emptiness, contraction, bounce, an eternal heartbeat. Now here is the detail that makes this theory so striking, and it connects directly back to where we started tonight. For this endless cycle to work, one specific thing has to be true. Dark energy, the force pushing our universe apart, cannot stay constant forever. At some point, it has to weaken, it has to fade, and eventually flip, so that expansion can slow, stop, and turn into contraction. Now think back to our very first crack, to Deci, and its hint that dark energy may already be growing weaker. Do you see it? A discovery in our own time, a machine mapping millions of galaxies, is showing us exactly the kind of behavior this ancient, eternal theory would need. That is why some scientists find this so exciting. It is a rare case where a wild idea about the deep nature of time makes a prediction we might actually be able to test. If dark energy really is weakening, it does not prove the cyclic universe, but it is a quiet nod in its direction. But there is something else about Paul Steinhardt that makes his story remarkable, and it tells you a lot about how honest science really works. Because decades ago, Steinhardt was one of the original architects of a completely different theory, a theory called inflation, which is, even today, the most widely accepted explanation for the birth of our universe. He helped build it, he is one of its founding fathers, and yet, over the years, Steinhardt became one of inflation's fiercest critics. He came to believe there was a deep flaw at its heart. His concern, put simply, was this. He argued that inflation is so flexible that it can be twisted to predict almost any outcome you like. And in science, a theory that can explain anything at all is, in a strange way, useless. Because a theory that predicts everything predicts nothing. It can never be truly tested, never truly be proven wrong. Think about what that took to help create one of the most celebrated ideas in all of physics, and then to turn around and challenge it, to spend years searching for something better. That is science at its most honest. Not defending your own ideas at all costs, but following the truth even when it leads away from your own work. And it was that search that led Steinhardt toward the cyclic universe, an attempt to explain the cosmos without needing inflation at all. And now let me keep my promise and be honest. The cyclic universe is a serious, carefully built theory, but it is not proven and it is not the mainstream view. Most cosmologists still favor inflation, but the cyclic model remains a real and living challenger, and the Deci hint has given it fresh life. So now we have two theories that both say the same startling thing, that there was a before, first a single bounce, and now an endless chain of them. But there is a third idea, stranger and more beautiful than either, one imagined by one of the greatest minds of our age, a Nobel Prize winner, and in his vision, the cold, dead end of one universe does not just lead to the next. It literally becomes the next universe's Big Bang. That is where we go next. So now we come to the most beautiful and the strangest idea of them all. It comes from Sir Roger Penrose, one of the greatest minds of our age, who won the Nobel Prize in 2020 for his work on black holes. His theory has a grand name, conformal cyclic cosmology, but the idea at its heart is pure poetry. Penrose imagines the universe living through endless chapters, which he calls aeons. Each aeon begins with a big bang, grows old, and dies, and then, out of its death, the next aeon is born. But the way one aeon becomes the next is unlike anything we have seen tonight, because in Penrose's vision, The cold, dead end of one universe does not collapse or contract. Instead, it transforms directly into the hot, dense birth of the next. Now, that should sound impossible, because the end of our universe and its beginning look like complete opposites. Let me show you the problem, and then Penrose's astonishing solution. Think about how our universe will end, far in the future. It keeps expanding forever. The stars burn out, the galaxies drift apart, and eventually, the only things left are black holes. But even black holes do not last forever. Over unimaginable spans of time, they slowly evaporate, leaking away their energy until they too are gone. What remains is a universe that is almost perfectly empty, cold, dark, and endless, filled with nothing but faint, scattered light. Now compare that to how our universe began, a single point, unimaginably hot, unimaginably dense, packed with all the energy in existence. The cold, empty end and the blazing hot beginning could not seem more different. So how could one possibly become the other? Here is Penrose's genius. He points out that in that final, empty universe, once all the matter is gone, something profound happens. There is nothing left with mass, and without mass, a strange thing follows. There is no longer any way to measure size or to measure time, because to measure anything, you need objects, clocks, rulers, things with mass to compare against. In a universe of nothing but massless light, those tools do not exist. And Penrose argues that when there is no way to tell big from small, the difference between enormous and tiny simply stops having meaning. And in that moment, something incredible happens in the mathematics. That vast, cold, empty universe, with no way to measure its own size, becomes indistinguishable from a tiny, hot, dense one. The two states, which seemed like total opposites, turn out to be the same thing, seen from different sides. The dead end of one aeon flows seamlessly into the fiery birth of the next. There is no bounce, no collapse, just a quiet, seamless handoff from one universe to another forever. Now, a beautiful idea is not enough in science. You need evidence, and this is where Penrose makes his boldest and most controversial claim. He says that if his theory is true, then the aeon before ours should have left faint marks on our universe. Specifically, he claims that giant black holes colliding in that previous aeon would have left faint, circular patterns, like ripples printed onto the oldest light in our own universe. And he says he has found them, faint rings, hidden in the ancient afterglow of our Big Bang. But here, I must be completely honest, because this is exactly the kind of extraordinary claim that demands care. Most cosmologists do not accept Penrose's evidence. When other scientists studied that same ancient light, they found that these faint rings can appear entirely by chance, purely from random noise, in a perfectly ordinary universe with no previous aeon at all. So the mainstream view is that Penrose is likely seeing patterns where there is only randomness. His theory is dazzling, his mind is extraordinary, but his claimed proof is disputed, and most of his colleagues remain unconvinced. Please hold it that way. A gorgeous idea from a brilliant mind, but not established fact. So we have now heard 3 daring theories, and all 3 say there was a before. But here is the twist you might not expect. Because even the mainstream theory, the widely accepted one, the very idea of inflation that most scientists favor, has a secret. When you follow its own mathematics honestly, all the way out, it too points to something beyond our universe. Something almost unimaginably vast. Not one universe before ours, but countless universes, all around us, right now. And that is where we go next. So let us turn to the mainstream theory itself, the one most scientists actually favor. It is called inflation, and it was first proposed by a physicist named Alan Guth back in 1980. And the strange thing is, Even this widely accepted idea hides a before inside it. Inflation was invented to solve a genuine puzzle. When we look at the oldest light in the universe, we find something that should be impossible. Two regions on opposite sides of the sky, so far apart that they could never have touched, never have shared heat, are almost exactly the same temperature. How can two places that have never met be so perfectly matched? It is like meeting two strangers from opposite ends of the Earth and finding their body temperature identical to 1,000th of a degree. Guth's answer was inflation. He proposed that in the very first sliver of a second, far less than the blink of an eye, the universe underwent a burst of expansion so violent, so extreme, that it ballooned in size by an almost unimaginable amount. And here is the key: before that burst, the whole universe was tiny enough to be in contact, to even out, to share the same temperature. Then inflation stretched that already matched patch into everything we see. It solved the puzzle beautifully, and it made other predictions that we later confirmed. That is why inflation became the leading theory. But when scientists studied the mathematics of inflation closely, they found something they did not expect, something that troubled and thrilled them at once. It appears that once inflation starts, it may never fully stop. Here is what that means. In most places, inflation ends, and a universe like ours settles down and forms. But in the wider space beyond, inflation just keeps going, expanding furiously. And within that endlessly inflating space, every so often, another patch stops inflating and forms its own universe. And another, like bubbles forming in an endlessly boiling, infinite sea. Each bubble is a complete universe of its own. Scientists call this eternal inflation, and it leads to a staggering conclusion. Our universe is not the only one. It is just a single bubble in an endless ocean of other universes, a multiverse. And the strangest part is this: in each of those other bubble universes, the basic laws of physics might come out differently. Different strengths of gravity, different particles, different constants woven into the fabric of reality. Most of those universes might be lifeless or unstable, or utterly unlike anything we could imagine. Ours might just be one rare bubble where the numbers happened to line up in a way that allowed stars and planets and us. So even the mainstream theory, followed to its honest conclusion, says there is something beyond our Big Bang. Not one universe before ours, but countless universes existing alongside us right now. But now, let me keep my promise one more time, because there is a beautiful piece of honesty here. You might think eternal inflation removes the need for a beginning entirely. If universes have always been bubbling up forever, then maybe there was never a first moment at all. But 3 scientists, including Alan Guth himself, one of inflation's own creators, proved something humbling. They showed, with careful mathematics, that even eternal inflation cannot be stretched infinitely into the past. That the whole bubbling process, however vast, must itself have had a beginning. Think about the honesty in that. Guth helped build inflation, and then Guth helped prove that his own theory still cannot escape the deepest question. It does not banish the beginning, it only pushes it further back into a fog we still cannot see through. And so we arrive at the humbling truth. We have now heard 4 of the greatest ideas in modern cosmology: the Big Bounce, the Cyclic Universe, Penrose's aeons, and the multiverse of eternal inflation. Every one of them, in its own way, whispers that there was a before, and yet not one of them is proven. Each one still leaves a piece of the mystery untouched. So after all of this, what is the real answer? What was actually there before the Big Bang? We have gathered the theories and heard the boldest minds of our species. Now it is time to stand back, face the question honestly, and ask something even more important. Not just what the answer might be, but whether we could ever truly know it. And that is where we end. So we have reached the end of our journey, And it is time to be honest about where we have arrived. After all the theories, all the brilliant minds, what is the real answer to what came before the Big Bang? The honest answer is that we do not know, not yet, but everything we have seen points toward a few great possibilities. Maybe a single universe came before ours that collapsed and bounced into being. Maybe there is an endless chain of universes expanding and contracting forever. Maybe the cold death of one quietly becomes the fiery birth of the next without end. Or maybe ours is one bubble among countless others, in a multiverse too vast to picture. We cannot yet say which is true. Perhaps none of them. Perhaps something no one has imagined yet, and there is a hard truth to face. Whatever came before, if anything did, may be sealed away from us forever. The Big Bang may have wiped the slate clean, and every telescope we build can only ever look forward, from the Big Bang onward. Looking past it might be beyond us, not just today, but always. But here is where the story turns, and where it becomes genuinely thrilling, because we are not standing helpless at that wall. For the very first time in history, we are building the tools that might let us peer around its edge. Remember our first crack, dark energy. Right now, DESI is still mapping the cosmos, and in the coming years it will tell us with far greater certainty whether dark energy is truly weakening. And if it is, that alone would breathe life into the cyclic theories and reshape our picture of the beginning. A new space telescope called Euclid is now mapping the dark universe across billions of light years. And the Vera Rubin Observatory has begun scanning the entire southern sky night after night, building a record of the cosmos more complete than anything before it. These machines are not science fiction. They are switched on, working, gathering the data right now. And there is one more tool, perhaps the most extraordinary of all, because there may be a way to hear an echo from before the wall. When the universe was born, some theories predict it would have rung like a struck bell, sending out ripples through space itself. Ripples we call gravitational waves, and these primordial waves, if they exist, would have left a faint, specific twist in the oldest light of the universe. A signature written into the afterglow of the Big Bang. Scientists around the world are hunting for that twist right now, and if they find it, it would be like reading a message from the first instant of time, a message that could finally tell us which of these theories is closer to the truth. So think about the moment we are living in. For the whole of human history, the question of what came before the beginning belonged only to philosophers and dreamers. It was a question you could ask, but never answer, and now, for the first time, it is becoming a question we can test. We are the first generation to hold the instruments that might actually see past that ancient wall. The wall, at long last, is beginning to turn into a door, and that is the real gift of this journey. Not a final answer, because we do not have one yet, but something rarer and in its own way greater. The knowledge that a species living on a small planet, around an ordinary star, has looked all the way back to the first moment of everything, found the exact place where its knowledge ends, and instead of turning away, has started building the tools to see beyond it. That is not smallness. That is one of the bravest things any creatures have ever done. So the next time you look up at the night sky, remember what you are part of. A universe that may have been born from another, and another before that, stretching back into a mystery we are only now learning to read. And remember that you are alive at the exact moment we began, at last, to ask the question with real tools in our hands. Thank you for taking this journey to the edge of time with me tonight. If it gave you a sense of wonder, share it with someone who loves to look up and ask the biggest questions of all. And if you would like to keep exploring the deep mysteries of the cosmos with us, every Wednesday and Sunday, you know what to do. Until the next journey, rest well, keep wondering, and never stop looking up.